lifetime buildings. If you remember last time, we discussed extensively about seismic design of timber structure, capacity-based design of light frame, capacity-based design of cross-laminated timber. Today we want to see what are the provisions if you want to do a capacity-based design of a light frame building. So, also for a light frame building, we need to design it in such a way that it will act at the greater possible extent as a box type structures. So, meaning that, as we already discussed for a cross-slab building, we need to make sure that we will avoid any sort of out-of-plane failure of the walls making the structure itself. Most importantly, the connections devoted to the dissipative behavior are only the nail connections between sheathing material and timber frame in shear walls. And to ensure the development of cyclic yielding in the dissipative zones, all other structural members and connections shall be designed with sufficient overstrength. So basically, if this is the structure that we are talking about, the idea is that only basically this connection, the connection at the perimeter of the sheathing, between the sheathing and the frame, with this connection indicated in red, only those nail or screw connection will be designed as a dissipative one. Meaning that when we are going to calculate the seismic forces using the design spectrum, which is given by the elastic spectrum divided by the Q factor, that in this case is equal to 5, those forces will be used only to design those connections, while instead all other members will have to be designed for the overstrength of those connections. So this means that all the other members, we will have to start from the actual strength of a single nail. So we will start by calculating the strength of a single nail, the actual strength. And from the actual strength of the single nail, we will then multiply this strength by the overstrength factor, that in this case is equal to 1.6. And then from the equilibrium, we will go to calculate and to design all the other members of our structure itself. So in other words, this nail, the nail connection between the frame and the sheathing, is what we were basically considering as the hinge connection, so actually the plastic hinge in the beam that you design in your reinforced concrete frame during the course of reinforced concrete design. So reinforced concrete design, you design for bending the section of the beam at the intersection with the column using the design spectrum, and then after, from the equilibrium, from that value, you basically recalculate all the shear and the forces in the columns, in the beams. So in this case, we will start from, as we said before, we will start from the actual strength of a single nail here, and from the actual strength of the single nail multiplied by the overstrength factor of 1.6, we will just work out all the values of the stresses and forces in all the other structural members, and in order to make the verification of the other structural members. So this means that, for example, the hold down, unlike the cross-slab panel that we saw yesterday, where the hold down, the connection between the hold down and the panel is a dissipative connection, in this case, the hold down will entirely be considered as a brittle element that will entirely be designed using capacity-based design. Also, the anchor bolts will be designed for the overstrength of the nails. The wall frame itself, so the framing will be over-designed. The sheathing will be over-designed. The sheathing used for the flooring system. The perimeter beams, the blocking, the joist. And also the nail connection between the sheathing and the framing in the floor will be designed for the overstrength of the nail connection of the wall. So now, how should we calculate those forces using capacity-based design? As I said before, we have a shear wall like this, where we apply a horizontal load P, which is the seismic load, we already said that this wall will act as a basically as a cantilever. So the bending moment, the overturning bending moment, which is given by the horizontal force P by the distance h, will be equilibrated by this resisting, stabilizing bending moment here, which is basically the tensile force into the vertical stud times the distance between the two studs. So by the equilibrium, P over h divided by B will give us this equilibrating tensile and compression force. And then, if you remember, from the equilibrium we can also get this shearing force in the bolts and also the shear force in the net. So in the end, the idea is that when it comes to designing a knife frame wall, we will only calculate the nail, we will only design this nail connection between the sheathing and the framing under the seismic force P derived from the elastic, from the design spectrum, which is given by the design spectrum, which is given by the elastic spectrum divided by the Q factor of 5. So ED, if you want, ED is the shear demand in this nail. So the shear demand in this nail from the equilibrium is the horizontal forces P times the spacing of the nail divided by B. If you remember, we already studied the equilibrium of this system, and we found out that, of course, if I know P divided by B, the width of this sheathing will give me this shear per unit length, P. The shear per unit length is the same on those two sides, because you remember that the shear forces are always the same, in the sense that there is this thing that this Cauchy tensor is diagonal with respect to the, it's symmetric with respect to the diagonal, so those two forces are the same, so B is the same here and here. The B in this side is basically the tensile force divided by H. So in the end, from the equilibrium, the strength demand in one nail, ED, will be V, the shear force per unit length, times the space. So it's P times S divided by B. So when it comes to designing a structure like this, we will calculate the lateral forces due to the earthquake using the design spectrum, which is the elastic spectrum divided by the Q factor, equal to 5. Then we design these nails for this spectrum, and then all the other members will have to be designed for the overstrength of this nail. So basically, once we have designed this, we need to calculate another force here, which is in equilibrium with the actual strength of the nail amplified by the overstrength factor. So it's basically the same process that you did for the frame, reinforced concrete frame, when designing for shear. You didn't design for the shear, your frame. If you remember, the beam of your frame in reinforced concrete was not designed for the shear coming from subtotal. It was designed from the shear equilibrating the actual bending resistance of your plastic hinge multiplied by the overstrength factor. Okay, if you remember. Here we need to do exactly the same, but in this case the dissipative member is the nail. So we start from, first we design the nail, then we calculate the actual strength of the nail, shear strength of the nail, we multiply with the overstrength factor, and then by the equilibrium we design all the other members, not for the seismic force P, but from the force which is in equilibrium with the actual shear strength multiplied by the overstrength factor. Okay? So this is the procedure we have to follow. So, what is the actual shear strength of a nail? The actual shear strength of a nail is summarized by this equation. So it's the characteristic strength that can be calculated using the Johansen equation, so the Euro equation, times modification factor K mod divided by gamma n, and times NEF over n. If you remember, this coefficient takes into account the fact that if we have more nails on the same line, the actual capacity of this group of nails is not n times the capacity of a single nail, is slightly less. So this coefficient takes into account this kind of thing. So we said before that ED was calculated with this relationship, where P, horizontal force, is calculated from the design spectrum as D equal to the elastic spectrum divided by Q. Once we have designed the nail, we reassess the strength of the nail with this formulation here. We multiply FD. We have to multiply FD by the gamma factor, by the overstrength factor, gamma RD, which is 1.6. And from the equilibrium, we are going to calculate again C, T, V, and all the other forces acting on this member here. So if you want, this is true when we design the nail, and then we need to use another step. Once we have designed the nail, I need to recalculate the strength, Fd, with this formula here. Once I know the strength, I need to recalculate, if you want, the shear, the design shear. The design shear is Fd over S. So for the equilibrium, this is the actual strength. For the equilibrium, this is the shear force per unit length between the stud and the sheathing. Then the shear forces are the same, and then for the equilibrium I reassess the value of the horizontal seismic force, which is not the actual seismic force. This is the horizontal force which will cause the nail to have this strength, this force here, Fd. So I'm applying now capacity-based design. So I know the strength, and from the equilibrium, I'm going to calculate all the other member, all the other forces that are in equilibrium with this force here. Okay? So for example, PD here will be VD times B. So PD is also given by Fd directly. So if I know the strength of the nail, the actual horizontal force that will induce this shear force in the nail will be Fd times B divided by S, the spacing. Okay? Now, suppose that I want to design, for example, this member which is subjected to this stud, which is subjected to tension. What is the force that I should design this member for? So, the force here, the tensile force, will have TD, will have to be the force which is in equilibrium with the actual strength of the nail. What is the force that is in the equilibrium with the actual force in the nail? So, we know that from the equilibrium here, the force here will be PD times H divided by B. So we can write we said that we want to study, want to design in tension this member. So we call TD the axial tensile force of this member, and we have to start from basically the shear force acting into a single nail. So the resistance of a single nail is given by Fd. We said that Fd is equal to N EF over N times K mod times FVRK divided by gamma M. So we calculate this equation, which is the shear strength of a single nail, where VRK is calculated with the Johansen equation. Okay? once I know FT from the equilibrium over this member, so TD will be VD times H, where H is the height of the wall. VD is FT divided by S times H. Okay? So, to design this stud subjected to tension, since this stud has a brittle failure mode, because tension is a brittle failure mode, I cannot design the member, this tensile member, by basically the actual seismic force, but I need to design this tensile member for the overstrength of the nail connection. So if the nail connection has this actual strength, I will have to design my, let's say, design value, so ED, which is the seismic demand on the tensile member, will be given by gamma RT, which is the overstrength factor of the nail, 1.6, times TD, which is the axial force that I have in this member, which is in equilibrium with the shear force that I have in the nail. So it will be gamma RT times FD H divided by S. So this became the seismic demand of the stud. Of course, the seismic demand of the stud shall be less than or equal to the resistance of the stud. And the resistance of the stud will be the area of the stud times Ft0P. Design strength of the timber stud parallel to the grain. Okay? So this is the verification that we have to do on the stud. Okay, it's clear? So in this way we apply capacity-based design to our timber structure. And the same thing, the same concept shall be applied also for the sheathing, for the plate, and for the bolts connecting the base of the plate to the foundation, for the on-down, and also for the floors that we have above. So everything must be designed for the overstrength of the nail connection. Okay? Now, we said that this nail shall be able to dissipate energy in order to be able to use the Q factor of 5. How can we ensure that this nail will dissipate energy during an earthquake? We have different possibilities. Two possibilities basically. The first possibility is just to check the nail slenderness. Just to check that if the nail slenderness satisfies the condition given by the Eurocode 8. So basically, we need to make sure that if this is the sheathing, and this is the stud, if this is the nail, this is D, diameter, and this is T, the thickness of the sheathing, as you can see. T shall be greater than or equal to 4D, and D shall be less than or equal to 3.1 millimeter. If I satisfy this condition, then I can use Q equal to 5 when calculating my design spectrum. to design the nail itself. If instead I have T greater than 3D and D less than 3.1 millimeter, in this case Q is equal to, as you can see here, 4. Okay? I have these two options. Note that the Q factor will be used only to calculate, only basically to design the nail itself, because the Q factor will be used to calculate the design spectrum, which is the elastic one divided by Q. But the elastic design spectrum will be used in the end only to design the nail, because all the other members will actually be designed for the other strength of the nail. Okay? The other possibility is just to ignore these limitations and just to go to see in Johansen equation which kind of failure modes will occur on the nail. So if the failure modes characterized by only embedding are governing the design, in this case we cannot consider the structure as a dissipative, we need to use a Q factor of 1.5. Okay? Instead, if we have a failure mode characterized by one plastic hinge formation, then we can use Q factor of 4. If we have two plastic hinge formations, then we can use a Q factor of 5. Just remember that there is also this relationship to satisfy. So in order to say, okay, my structure is dissipative, for example, I use a Q factor of 4, I need to make sure that those two modes, so the minimum of the strain capacity of these two modes, will be sufficiently distant from the minimum of the shear capacity of those three modes, which are brittle, using this kind of safety coefficient 1.2. Okay? Also for the shear, also for the light frame wall, I have this requirement that if I want that the building is able to dissipate a lot of energy in order to use a Q factor of 4 or 5, I need to make sure that there will be a dissipation spread around all the structure, not only one story. Because otherwise I have a localization of the energy dissipation. One story I have what we call as a weak flow mechanism. Instead I want to have a distributed plasticization. To have a distributed plasticization, like for the cross-lamp building, like we said last time on Monday, we need to make sure that the ratio between the shear strength demand and the shear strength capacity, so the red and the blue curve, so the ratio between the two, should be more or less constant at each floor. So there shouldn't be some significant differences between the two. Okay? So it must be this constant here, more or less constant, so no significant difference. Because only this way we can have a full plasticization, then in the case of cyclic behavior, we can have significant energy dissipation. Okay, any question about the capacity-based design of light frame buildings? Okay, now just one perhaps small comment on modeling of timber buildings, particular modeling of cross-lamp buildings. So if several experimental tests were performed on cross-lamp buildings connected, you see, to the foundation using connector methods. And in all the cases, it was shown that usually the distortion of the wall itself, so the shear distortion or the bending deformation of the wall itself, were negligible, you see 2%, compared to this kind of rigid deformation. For example, rigid rocking, 42%, or rigid slipping, 56%. So this is important to keep in mind that if we want to model a cross-line building using the finite element modeling, for example using SAP 2000, it is crucial to model the connection flexibility. So it's not enough to use some millions of shells to model the floors and the walls, if after we assume that the shells are glued to each other, so the wall is glued to the floor. So this is not what happens in the reality. Actually, floor and wall panels, so the floor and the wall panel can be considered as an in-plane region. However, it is crucial to model the flexibility of those connections here. So we need to introduce some springs, usually, with SAP 2000, to schematize, for example, the hold-down or the under bracket. So we need to use some springs to take into account the flexibility of those connections. I just give you just this hint because, at least for this course, I'm not asking you to do a finite element modeling of the whole building because it will take too much of time. So last year I gave also some advice on how to model the hold down and so on, but this year we don't have time, and so I would just say this: in the future, if you will be asked to design a multi-story timber buildings, and you will have to do a finite element model, just keep in mind it's not enough to use shell elements glued to each other, so floor and wall, glued to each other without any disconnection. We need to take into account that those connections are flexible, because you see that those two components of the formation account for 98% of the total deformation. While instead, by using shell elements for wall and for the wall and the floor, you will just account only for the 2% if you don't model this flexibility here. So just keep in mind that if you have to in the future to model multi-story timber buildings, it's okay. You can also use the shell elements for the wall, but then you need to remember you need to model with springs these connectors here, because otherwise it doesn't make any sense your model that you are using. Now instead, what I would like to see with you is a simplified by-hand analysis of a small building, which is more than enough if you have to model a small timber building. So, we want to discuss shortly, since you haven't done yet any exam about seismic design, how do you calculate, if you have, for example, a building made from different walls, how do you calculate which is the amount of shear that each wall attracts from the total seismic force? Because so far, what you've done is you know how to calculate the seismic forces at the different levels using the linear static analysis. This you've already done in reinforced concrete construction. Then you can also know how to calculate the shear force, the story shear, by adding the shear that you have above a certain plane. But the problem is, how can I calculate how much of this total story shear will go in the different walls that makes my structure? In reinforced concrete construction, how do you calculate, once you assess the total seismic force, the force that was attracted by each frame in your structure? Remember? You should remember. No? Yes, you did what is called a kind of matrix analysis, because you had also some walls, if I remember well. So you built your the stiffness, a different story of the frame and the walls, and then by doing this analysis based on the stiffness, you could understand how much of the total seismic force was applied, for example, to the frame that you decided to design. Okay? So now I would like to discuss with you how to do the timber. So how to calculate the stiffness. because as I said before, of course, if I know the stiffness, then it's relatively easy to calculate. But which stiffness do I need to know, and how do I calculate the stiffness of a light frame wall, for example? So, another important thing I want to share with you is this, that in reinforced concrete design, you made an important simplification, which is actually true for a reinforced concrete floor. So you assume that the floor was in plane rigid in order after to calculate the distribution of forces. Now, is it true that for a timber multi-story building the floor can be regarded as in plane rigid? Because of course, if the floor is in plane rigid, in direct proportion to the stiffness of the shear wall, this for sure, hold. Suppose for a moment if you have a very flexible diaphragm. For example, if you are designing an old buildings made of masonry with a timber floor made by joists and just one layer of boards, planks, for sure this is not an in-plane rigid floor. This is closer to say to an infinitely flexible floor, at least in plane. So if I'm talking about a flexible fall diaphragm, in this case, the seismic shear will be distributed between the different walls in direct proportion to the tributary area and mass of the floor of the shear wall, not using the other criteria. Okay? Now, in a multi-story timber buildings, we have timber floors that we said in the seismic region should anyway be made by sheathing, not by walls, by narrow walls, but by sheathing nailed on all the perimeters. So I have something which for sure is not infinitely flexible. So it's in some way it's stiff, but is it infinitely rigid? In the reality, I would be somewhere in between rigid and flexible. If I'm somewhere in between, then that will make this problem of lateral load distribution very complex to solve. So what we need to do, we need to find some kind of simple solution. For example, if I want to account for the flexibility of the floor, the in-plane flexibility of the timber floor, how should I do it? Well, I should, in some way, model the vertical. I should model, let's say, the vertical shear walls with a spring, schematizing the flexibility of the wall. And then I should model also the flexibility of the diaphragm itself, which is very complex. Because you see, the diaphragm in this case is modeled as a continuous beam. Continuous beam that rests on a number of flexible supports schematizing the vertical walls. Now, in order to understand the stiffness of this spring, so the stiffness of the vertical walls, I need to see what are the different components of flexibility in a shear wall. If I consider a shear wall and I apply a lateral force on top of the shear wall, as you can see, I have different components of deflection. The first component of deflection comes from the distortion of the panel. So what we call sheet shear. So the distortion of the panel will give us the first component of deflection. Then we have the slip between the nails and the sheathing. So the flexibility of the sheathing to frame connection. This will give us another component of deflection. Then we have what we call rigid body rotation. So the wall could basically rotate rigidly due to the fact that we have a stretching on one side, for example, go down, and we have a squashing on the other side, timber. And finally, we have a global flexural behavior due to the fact that we have one star which is stretched and the other one which is compressed. So, we could say that all those components should be added in order to get the total deflection, in order to get the value of the flexibility. So basically, if you want the stiffness of the spring here, that we should then use to calculate in this model the distribution of the seismic force into the different walls. Okay, if we do some analysis, you will find that there are different, of course, percentage between these different components, but as you can see here, the nail slip is usually very important. So nail slip counts for 59–60%, paddle shear only 1%, base rotation 28%, flexural deformation 12%. Okay, now if you look at the chord regulation, you won't find any formula to calculate the deflection on top of a shear wall, neither in the Eurocode 5 nor in the Eurocode 8. For the future, for the new generation of the Eurocode 8, actually the Eurocode 5, there will be some formulas that will be added. For the time being, the only available formulas are the ones that you can see here that are taken from the New Zealand standard. So basically the design standard of New Zealand, which was in some way copied almost by the Canadian New Zealand standard. So in the end, this formula were more or less the same in the Canadian standard and the New Zealand standard. So in this formula, as you can see, we have that the total deflection on top of the wall is given by the sum of 4 components. First component is chord relaxation and base connection. So this will be basically the rocking, the rigid rocking. Then we have a shear the distortion of the sheathing. Then we have nail slips, and then we have this bending flexibility. So here you have the explanation of the symbols. So with this formula, we are able to calculate the top floor, the top wall displacement due to the horizontal seismic force. Of course, when it comes, for example, to the nail slip, the nail slip deformation depends on the slip that they have, of course, in the nail, EM. And the slip that they have in the nail is the shear in the nail times, well, sorry, this is V is actually not the shear, V is the seismic force times S nail spacing divided by the breadth of the wall and divided by the slip modulus of the nail itself. Where the slip modulus of the nail itself can be calculated with this formula, same empirical formulation you can see here. So at the end, in order to calculate the distribution, the seismic force between the different shear walls, I should model the diaphragm as a continuous beam, the walls as an elastic spring, and the stiffness of this spring should be given by the horizontal force divided by the total deflection. But then, as I was mentioning before, we would have another problem related to the fact that the diaphragm is not really a continuous beam. By the diaphragm, we should take into account that there is also a component of deflection due to the nail slip of the diaphragm itself. So, in other words, if this is the beam, if this is the diaphragm, and I load the beam with horizontal forces due to the earthquake, I will end up with a deflection, horizontal deflection, which is the sum of 3 components. So delta 1 is the flexural deflection of the diaphragm considering the course acting as a moment against the couple. So if you want, delta 1 is the deflection due to the bending moment. Then delta 2 is the deflection of the diaphragm resulting from shear deformation and sheathing. So delta 2 is the shear deformation. And this is what we always have in a beam. But then what we are missing out in this case, we have a third component deflection, delta 3, Delta 3 is due to the fact that these sheeting are not glued on the member, but they are connected with flexible connection. So they're connected with nails. So we have a further increase in deflection related to the nail slip. So the slip in the nails connecting the sheeting with the floor itself. Of course, modeling this sheet nail slip is not trivial using some 2000, for example. It will be very complex. So in the end, as you can see, the problem seems to become fairly complex to resolve. Furthermore, I have to tell you another important thing, that in a building made of light frame, made of timber, usually you have also some partitions inside. So non-structural partitions. Those non-structural partitions, for example, some partitions made of gypsum plasterboard, are usually neglected if we have a reinforced concrete construction, because the stiffness is much lower compared to the stiffness of the reinforced concrete frame. But in this case here, the stiffness of a gypsum plasterboard is not much lower as the stiffness of a shear wall. So they have some value in some way comparable. Meaning that if we ignore the stiffness of this gypsum plasterboard, as we usually do, we are losing one component of the stiffness of the structure, which is more or less the same as the other, not much different. So in the end, you see, in the end, for the sake of simplicity, we do a very rough approximation, usually, when we design a multi-story timber building. What is this rough approximation? We assume that the diaphragm are rigid, so the floor diaphragm are considered as a rigid. And then we assume that the lateral force is distributed in proportion to the length of the shear walls. So rather than we count the proportion to the bending stiffness of the frame of the wall, like we were doing, for example, the routine for reinforced concrete design. In this case, we assume that the shear force will be distributed, the seismic force will be distributed in the walls according in proportion to the length of the shear walls, as if the force was proportional to the sheet shear and nail slip stiffness. If you look at the formula for the sheet shear and the nail slip stiffness, you will find that in this case, those two components of deflection are in some way, those two components of stiffness are proportional to the length of the wall. So, suppose you have to design a building like this, where in yellow you find the structural resisting wall. So, this is a building made of light frame construction, for example, and in red you have the light frame walls which are considered as a structural one. You see that there are also some other smaller walls, but those smaller walls are not considered because they are too short. So a wall, in order to be considered for seismic resistance, should be at least 60 centimeters long. So, first of all, we said we calculate the horizontal force. So Fyi is the seismic force applied in the direction parallel to y on a certain story I. So this force should be applied in the torsional, in the center of stiffness of our system, in order to produce only a translation, a displacement, a rigid displacement of the floor itself. So, how can we suppose that we have this horizontal seismic force applied in the center of stiffness of the wall? So, if this is applied in the center of stiffness, it means that we will have a pure displacement without any torsional rotation of the whole building. So, how do we calculate now how much of this total seismic force we'll get in a general J wall at the floor I? we said before that VFYIJ will be proportional to the length of this wall. So what we do, if this wall has a length LYIJ, we can say, okay, VFYIJ, so the seismic force here, the shear force here, will be FYI, the total force, multiplied by the ratio between the length of the wall and the summation of the length of the whole structural walls. Okay? So as you can see, the criteria is quite a simple criteria. It's a very simplified criteria. But then, of course, what we said before, this is true if the seismic force is applied in the center of stiffness of my wall. However, usually, the seismic force is not applied in the center of stiffness, but is applied in the body center, the center of the masses. So in the centroid of all the masses. So in this case, for example, will be more or less in the center of this rectangle. If there is an eccentricity between the center of the masses and the center of stiffness, of course there will be also a torque moment. Not only a shear force, but there will be also a torque moment. Okay? So it's very important that we are able to assess the center of stiffness of our wall system. How can we calculate the center of stiffness of our wall system? The center of stiffness, in this case, will be the centroid, since the stiffness is proportional to the length. The center of stiffness will be the centroid of distribution of lengths, like this. So, what we do, we can say, okay, if this is the origin of our X and Y reference system, let's say Xij be the distance of the generic wall from the origin, and let's call XCTI the distance of the center of stiffness from the origin of the axis. Then we can write down, we can use the normal format that you use to find out the center of mass. So, if you want to find the center of mass is basically the first moment of area of my figure with respect to the origin divided by the total area. So in this case will be the summation of the length of each wall multiplied by the distance from the origin divided by the summation of the length of each wall. Okay? So in other words, the center of stiffness can be regarded as the centroid of a system of masses where each mass is basically the length of a wall. Okay? It's clear this? Okay. Of course, in this way I can calculate the distance of the center of stiffness parallel to X, and then also the distance of the center of stiffness parallel to Y. By using this case, by considering this case, not only the walls which are parallel to Y, but also the walls that are parallel to X. So, we need just to keep in mind that each of these walls will provide a restraint only parallel for displacement parallel to the plane. So, what does it mean? That this wall here can provide a reaction only in the plane of the wall. It cannot provide a reaction perpendicular to the plane. So when it comes to reacting to a seismic action acting horizontally, only the walls which are acting horizontally in the other direction will provide a restraint toward movement. So when I calculate the distance of the center of stiffness parallel to Y, I need to consider the walls that are basically parallel to Y. Okay, it's clear this? Good. So once I know the center of stiffness, then I can calculate the seismic torque moment. Because I know the center of mass. If I have a rectangle, the center of mass will be the center of the rectangle. If I have a figure like this, the center of mass will be the center of this figure here. So it will be a bit more than closer distance from the center of mass of this rectangle. So, the seismic action is actually applied in the center of mass. So I can say, if I apply a seismic action in the center of mass, what does it happen? It happens that there will be, you see, an eccentricity between the center of mass and the center of stiffness. So this is equivalent to having one seismic force applied in the center of stiffness, which will induce only translation in the wall, plus a torque moment given by Fyi times the eccentricity, which will induce a torsional rotation in the floor. So if the seismic force is not applied in the center of stiffness, there will be translation plus rigid rotation. Okay? And the rigid rotation is due to this torque moment. Now, how can I calculate now the shear forces induced in the shear walls by the torque moment? By using exactly a similar formula as the one that we saw before. So if this is, you see, is the torque moment, Mi. If I consider a generic wall of length Lyi, if this wall is distant xij minus xcti by the center of stiffness, then this seismic force here will be proportional to the distance of the wall from the torque moment. So the farther the wall, the higher the force. It will be, so basically Vmyij will be Lyij, which is the length of the wall, divided by the summation of the length of the whole wall multiplied by the distance from the center of stiffness, and everything multiplied by the torque moment. So this, if you look at this formula here, is formally the same formula that we derived when we calculated, if you remember, the shear forces acting into a bolted connection with the bolts distributed in some way in a connection region. Okay? If you go back to see, for example, remember you have a connection like this with a number of bolts, and we had a bending moment for the beam, which was a torque moment for this connection. We derived some formula to calculate this, the value of this force, the shear force in the bolt connection. And those formulas you can see here, they are very similar. The only difference being that in this case, in this case, the bolts are different, they're not the same size like that. So in this case, we have that the distance of, let's say, of the shear wall by the center of stiffness is multiplied by a number which represents the length of the wall. So for the bolts, in the end, we had we had a formula that was similar to this, with this slightly different that you can see here. Okay? And this is based again on the hypothesis of in-plane rigid floor. Yes?
Ma perché c'è sul denominatore sia per la y la componente y che per la x la componente y, cioè non dovrebbe essere rappresentato da xg meno xgt.
No, because in this case, while before for let's say for the seismic force applied in one direction, the only acting, for example, for the seismic wall applied parallel to y, only the yellow wall are active. Instead, when you apply a bending moment, a torque moment, all the walls are active. Because you see, for example, in order to get this bending moment, this torque moment here, I have to do this seismic force here times the distance, plus also this force here times the distance. Yes, all of them must be consistent, exactly. Okay? So if you want, we have here, in the end, it's a kind of Navier formula where you have your bending moment divided by, in this case, we have instead of the second moment of failure here, we have a kind of, well, it's not really a bending moment because we have the length times the distance, not the length times the distance squared. Okay? So it's slightly different actually. Yeah. So basically you go to write an equation while you said that a general shear force which is proportional to the stiffness times the distance will give us the total bending moment M. Okay, so in terms of bending moment, if we have an eccentricity, we need to calculate with this formula here the value of the additional shear force acting on the wall to consider that this system of shear forces will have to equilibrate the torque moment acting on the structure itself. Okay? Then, of course, in the other wall, I will have the length of the wall, this time is Lxij, divided by this denominator, which is the same as before, multiplied by Ni. Okay? So, in the end, to calculate the total shear acting on a certain wall, I need to superimpose the shear force due to the load, due to the shear applied in the center of stiffness, plus the shear force due to the bending moment, to the torque moment coming from the eccentricity between the center of mass and the center of stiffness. This in both directions. Okay, we should also say that the same criterion can be used to design cross-lamped buildings. In a cross-lamped building, we use exactly the same criterion. In this case, we assume that the same type of angle bracket is used in one story. So when we design the angle bracket for one story, we should be using exactly the same angle bracket type. And also, the spacing between the angle brackets should be kept more or less constant. Allora, based on this hypothesis, we can say, okay, also for a cross-lamped building, we can use this simplified criterion and to distribute the shear and in proportion to the wall length. So in the end, if I have to design a multi-story building, which we will see also in the work example, For example, I have to design a three-story electrical building. What is the logical flow of calculation that I have to do? First of all, I need to calculate the base shear, B. The base shear is calculated using the design spectrum, so PV will be ST, which depends on the first vibration period of the building, times, that is, if I remember well, the lambda coefficient, times W divided by G, where G is the seismic weight of the building. Then, once I know FB, I need to calculate the inverted triangular distribution of lateral forces at a different story. 1, 2, and 3. Then I'm going to calculate the shear force. So the story shear. So the story shear will be here F3. Then here F2. F1. So this is the story shear. Okay? And then at a certain story, for example, at the base story here, I have the total shear, and the total shear would be, for example, the total shear would be Fy1, so Fy1, so this Fy1 will be the total shear at the base story. And with this formula, I'm going to calculate the center of stiffness, and then I superimpose for each wall. I superimpose the shear in the wall due to the total shear force applied in the center of stiffness with the shear in the same wall due to the torque bending moment related to the fact that there is an eccentricity between the center of mass and the center of stiffness. So in the end, for each wall, I can get this F and Y, JJ. So then, once I have this value, basically I know for each wall, so this is a generic wall, shear wall of the building. So for each wall of the building now, I have the value of forces 1, 2, and 3. So if you want, I have directly the shear in the end. So I have this one. So basically, from the total shear, from the total story shear acting on the whole building, I can calculate for each single wall of my building the distribution of shear. Okay? Which comes from this equation that we saw before. Okay? Once I know this shear value here, I can go and calculate, for example, in the light frame building, I can calculate the name. And then with capacity-based design, I can calculate all the other members. Or if I am in a constant building, I can use these formulas to calculate the tension forces in the hold down and the shear force in the upper brackets. And then capacity-based design for the other members. Okay? for example, if I have a vertical screw connection, okay, use this equation that we derived a while ago. Okay? Any question, please? So this is the procedure that we should follow to design a small lecture building or a small cross-laminated timber building. Now the last thing before we do a work example, to understand better, is how can we calculate the interstory drift? Because if you remember, when we do a circuit design, there is not only one designer ultimate mistake, but there is also designer serviceability mistake, what is called damage control. For damage control, what we need to do, we need to estimate the interstory drift, and which is the difference between, basically, if this is my building, if you remember, the interstory drift is this relative displacement. The relative displacement, okay, I should put here, the relative displacement that happens on the story of roof with respect to the story where I am. So, interstory drift are those relative displacements, those horizontal displacements. How can we calculate the interstory drift? So, we have some formulas. For light frame construction, we saw before that there are some formulas. So, all the formulas that we discussed before, taken from the New Zealand standard, can be used to calculate the interstory drift and to compare those values with the limit value for damage control limit state. For cross-laminated timber, there is no formula at all. So for cross-laminated timber, you can see here a simplified and very rough method that is based on the fact that if I have a cross-lam wall and I apply a lateral force, for example, a force due to the earthquake, in general, as I said before, I will have two predominant deflection components. The two predominant deflection components are the rocking component, which is basically this kind of rigid rotation around one corner, and then we have the slip of the wall, which is basically a rigid translation horizontal. Okay? Now, the total deflection that results from these two, from the superposition of these two displacement components, will be given by the sum of this horizontal displacement in the rocking deformation dE rock plus this dE slip, which is the horizontal displacement. Now, how can we estimate dE rock and dE slip? Now, dE rock, as you can see, this horizontal displacement is related to the uplift, the vertical displacement that I have at the all-down location. Okay? If this cross-lam wall was a square, I will get that, since this is rigid, I will get that this dE rock will be exactly the same as this uplift. Okay? If this one is not a square, then what I can do, I can relate dE rock to UHD, which is the stretching basically of the all-down, in this way. I can say that dE rock is UHD, so the uplift on the all-down, times H divided by B. Why times H divided by B? Because basically UHD, if you see this angle here, so basically these two triangles, 1 and 2, they are similar. Okay, so if I want to calculate dE rock, UHD divided by B, so UHD divided by B is basically the tangent of this angle here, which is the same as here. So I can say that dE rock is the tangent of this angle, which is exactly the same as this, times H. And then I can find this relationship, very simple, okay? Now, of course, this relationship has some sense if I can estimate UHD. can I estimate UHD? Well, I need to look at the hold down. UHD will be basically connected to the flexibility of the hold down. In a hold down, if I design an hold down using capacity-based design, remember when we said yesterday, actually 2 days ago, a hold down shall be designed using capacity-based design. So the idea is that a hold down should have the metal plate over design and also the bolt down over design in order to make sure that I will have plasticization only of this nail connection. Okay? So if I have over designed hold down, I can say that okay, the stretching of the bolt is negligible. The elongation of the plate is negligible, and what really counts is just the plasticization of the nails here. So that's basically not the plasticization, because I'm talking about damage in the stage, it's not the plasticization, it's the elastic deflection of the nail connection. So the elastic deflection of the nail connection can be calculated this way. So UHD is FHD, the force acting in the hold down, divided by the stiffness of the hold down. Now, ideally, I should have the producer of the hold down providing me with the stiffness value. So each hold down has a different stiffness because, of course, it depends on the flexibility of the metal plate, on the flexibility of the bolt, etc. Now, if the producer does not provide me with this value of stiffness, what I can do, I can say approximately the stiffness of the hold down will be given by n times, where n is the number of nails, n times the elastic slip of a single nail. Now, the elastic slip module of a single nail is rho m, so the mean density of the timber, to the power 1.5 times d divided by 23 times 2, because this is a steel to timber connection. So in other words, if you have a timber to timber connection, you will find that for one nail, this is the slip modulus. But then the regulation said is, if you have instead a steel to timber connection, take this value and multiply by 2. If you have n nails, multiply by n. Okay, so this, if you want, is a simplification in the case where the producer does not provide us with this KHD factor. So, FHD from equilibrium, the vertical force in go down, is THD times H divided by B minus the stabilizing bending moment, which is given by the vertical load applied above the wall. So in the end, with this simplified formula, I can calculate DE load. For DE slip would be the horizontal force divided by the number of angle brackets times the stiffness, the horizontal stiffness of the angle bracket. Now, if you consider an angle bracket, you can assume that the steel part was rigid, and the only flexible part are the nail connection between the angle bracket and the wall, and the nail or screw connection between the angle bracket and the floor underneath. In this case, of course, we have a system where it's like having two springs, a series of two springs, where one spring schematizes the nail connection with the wall, and the other spring schematizes the nail connection of the other bracket with the floor. So if this is K1 and this is K2, which are basically N1, as usual is again the elastic slip modulus of a single nail, which is rho n to the power 1.5 times d divided by 23, times 2 because it's still the timber connection, times N1, because we have N1 nails. So those two stiffnesses if I want to calculate the total deflection, U, so U will be F divided by K, which is the stiffness. But, so this would be the total deflection. But the total deflection can also be written like U equal to U1 plus U2. So U1 is the deflection of the first spring, is F divided by K1 plus U2, which is the deflection of the second spring, which is F divided by K2. And this is the same as F divided by K. So in the end, if you have two elastic springs as a series, you probably already learned from science, from mechanics of structure, that the relationship between the stiffness is 1 over K equal to 1 over K1 plus 1 over K2. Which means in the end that the total K is 1 divided by 1 over K1 plus 1 over K2. So this is why you can see here Ka. So the total stiffness of an angle bracket is 1 divided by 1 over KEL1 plus 1 divided by KEL2, where KEL1 is the stiffness, basically is the stiffness of the connection between the net connection between the angle bracket and the wall, and KEL2 is the stiffness of the angle between the angle bracket connection and the floor. Okay? So in this way you can calculate this value Ka, and you put inside it, you get the PE slip. Now this is a very simplified method that I just developed because the regulation cannot find anything. So if one day you have to design a colossal building, it's mandatory to check also the damage to the state, you need to have some formula to calculate this interstory slip. Either you do a finite element model, but again, it's not enough to use only the shell element. We need to then to model also those springs here, using those angle brackets that are now using spring. This is not very simple. Or you can use this simplified relationship to have at least an idea of what is the interstory slip that you can predict. And then you can compare with the demand, well, with the limitation, the demand given, sorry, with the limitation given by the regulation, like the direct regulation. Okay? Of course, if you consider the angle bracket connected to the foundation, then this stiffness, if the connection of the angle bracket to a reinforced concrete foundation can be considered as fully fixed. In the drawing elastic deformation. So in this case, Ka is just equal to KEL1, just the flexibility of this. So here you have some literature, but this is technical literature. I think what I gave you here is it's a good starting point. Then of course if you want to specialize yourself in designing big or large multi-story buildings, perhaps you need to do some search on the internet and do a bit of more study, okay? But at least for a small cross-laminated light frame building, what we saw so far should be enough. Also because now we are going to start, well, we don't have a lot of time today, we just start. I have two work examples, one of design of a small cross-frame building and one of design of a small light frame building, just to understand the actual procedure that we have to follow when designing these structures. Okay, one important thing, I just forgot, and I should have told you the day before yesterday, but anyway, many of you were absent the day before yesterday. We need to do the survey of the course. Okay, so tomorrow morning, please bring with you mobile, either a mobile or an iPad or a laptop. And with this one, you will connect to the website of the university. You will do the survey of the course. Okay? Because after we have okay, today, then we have tomorrow. And then I would like to do, as I mentioned to you last time, I would like to do on Friday a couple of hours, 2 or 3 hours, what is needed to complete the course, which means to complete the work example. Perhaps tomorrow we are able to complete the work example, I'm not sure, but we still need on Friday morning to do a couple of hours about fire resistance of timber building, which is a very important topic, because timber, as you know, is combustible material. So we need to know how we can, in some way, ensure a minimum of fire resistance for our timber structure. So on Friday morning, we will have, I know that you cannot, because we have the course with the Berardinis. We have to do this 4 hours, 3 or 4 hours, just to complete the program about the fire design. I think that tomorrow there was no chance, right? Because tomorrow we have 2 hours from 9 to 11 with you. After from 11 until the evening you are busy, right? All of you are busy. From 9 until the evening. Is true? Okay, in this case, and also today after 5 you have another course. So tomorrow you don't have anything in the afternoon? Tomorrow afternoon you have something? Yeah, but you for what time?
We have more lessons between about 11 a.m. and 3 p.m.
Yeah, no, but the other ones, then you have a lesson between? No, the other one they have from 9 to 2. No, the question is, do you have a lesson from 3 to 9 o'clock? No, 9 o'clock. 3 to 7 o'clock. You have a lesson. Okay, so the only way then is to do Friday morning. So Friday morning, all of you, except one person, unfortunately, are free, theoretically, except also you have to do the revision about the degree. Okay? What? Can you do an 8 o'clock immediately with what time do you have to do this?
Lo chiediamo e speriamo che poi presto.
No, I can phone later to Fabio and ask if you can do. So, what would be better, first or later?
First.
First. Ma what time do you start? The revision.
Teoricamente ancora non c'è possibile, però dalle 9 sempre quindi 8 anni no,
Sì, ok. No, perché in questo caso gli telefono e gli dico se magari può venire un pochino più. Magari adesso quando finiamo le lezioni, gli do subito col telefono, se può venire prima vi dico immediatamente l'ora, così fate subito voi 3 e poi venite a lezione. Va bene? Quanto tempo vi serve per fare sta? Ah, poco? Poco. Vabbè, lo facciamo così. Sì, sì. Ok, perfetto. Ok. So, okay, we have maybe 20 minutes, we just started. So this is a full work example of assembly design of a small cross-laminated multi-story building, which will give you an overview of the process that you should be following when designing this. In fact, as I know, I would like you to do a small additional work example, which is nothing to do in terms of, let's say, time committed to this compared to the other design project. The design project for the single story building will be fairly complex because we need to consider these 100 more long combinations. But I really would like that you do also a small project, one in one person, just following step by step what is presented here, which means a small building, 2 or 3 stories, no more, made either of crossland or of lightweight construction, okay? So for this one, I would like you just to calculate in this work example the seismic forces, then to distribute the seismic forces at a certain level between the wall, and then to design, let's say to design one wall. Just to have at least once after you follow more courses, of course, seismic design, but at least to see that you are able to follow step by step the different verifications. So I'm not asking to design the whole building. I'm asking to take a small building like this. Of course, at the seismic forces you have to calculate at different level. Then, to do this, what we said before, the way to calculate like the center of stiffness and the center of mass. So for example, for the ground floor, to redistribute the seismic shear in the different wall, and then to take one wall and to do the design of this wall. Okay, so it shouldn't take you, this kind of exercise shouldn't take you more than, I would say, 6 hours. Okay, well, it depends if you want to use Excel or put everything in Excel, this will take a little bit more. But for me, it would be enough to do by hand. Okay? Because I would like that you just are confident in following this design procedure you can see here. Okay? So, in the end, to do the design of one wall of a single building. So, let's go to see here, for example. So, this is a very simple building layout, as you can see. So, 3-story building made from different cross components. These are the walls. This is the floor. Seismic zone. For example, seismic zone 1, AG is 0.35 C. You can take also here. To save time, just assume that you have this building located at exactly the same point as the other building that you have designed. So you got the AG and what you need, and the type of soil. And you already got the elastic spectrum, basically. So you use the same elastic spectrum. The only difference being that here you are going to use a different Q factor. So the design spectrum here will be reduced compared to the other. Because the other you use a Q factor of 1.5. Here we're going to use a Q factor of 3 if there is, or 2.5 if there is a cross-land building. Otherwise, if there is a light frame building, 5. Okay? So, and in this case, soil type A. Topographical scenario building built on the top of a hill. Destination domestic, important coefficient 1.0. Here this one was calculated using Q factor of 3, which is according to the new Eurocode 8. In the reality, if you know, if you remember now, if you design cross-land building now in Italy, you have to use a Q factor of 3.5. Okay? Then, geographical region for the calculation of snow load. Okay, this case was Alba region, Udine, this you can put Aquila without any problem. The height you can put l'Aquila, so everything is ready. Regulation, in this case we use the Italian regulation, Eurocode 5 and Eurocode 8. So, first of all you need to do the load assessment, so the assessment of the loads. So, an estimation of the structural self-weight. Also here, don't lose too much time in this exercise, just take some reasonable value for the loads. Okay? Like the structural self-weight, 0.35 kN per square meter, for example. Non-structural permanent load, G2, which would be the layer, the floor, and so on, 1 kN per square meter. Total permanent load is the sum of these two, 1.35 kN per square meter. The snow, take exactly the same load that you already assessed for the other building, so you don't lose time, 1.2. Total variable load, 1.2. For the wind, just ignore the wind, because we saw it's better to ignore to avoid a problem. Okay, so we just ignore the wind, we don't lose time. So we just consider permanent load, snow load for the roof, and the seismic load, of course. So this was for the roof. For the typical floor, again structural self-weight, which depends in this case of the type of floor, cross-land floor that we are using, so 0.6 kN per square meter, no structural permanent load 2.96, total 3.56, and the variable load, if this is a residential building, is 2 kN per square meter. And then we have the wall weight, so the weight of the walls. So exterior interior wall, structural permanent, weight of the X-land wall. So it's 0.35, so 1 square meter of X-land wall is 0.35 kN per square meter. Then per total per meter of length, 0.35 times the height of the wall. times 2.95, 1.03, this is the weight of the wall per unit of length. Okay? Then I have non-structural permanent load, which is the weight of the thermal insulation finishings on 6 per square meter. Again, 0.6 times 2.95, 1.77 per meter of load. So the total permanent load per meter of length is 1.77 plus 1.03, 2.8 kilonewton per kilonewton per meter. Then what we should be doing, we should just keep in mind that in order to be able to do a linear static analysis, the building should be regular in plan. So here I have summarized the regularity in plan criteria. In your case, please consider a regular building. Otherwise, theoretically, we could not use this analysis to do a dynamic analysis, which we don't want to do. Okay? So the criteria, you see the different criteria. The plan is compact and almost symmetrical. Of course, this you are going to learn all about this in the seismic engineering course, where you will discuss a lot about next year. We will discuss a lot about regularity plan, regularity elevation, and so on. For the time being, I just listed here for you to consider. So the plan is compact and almost symmetric along two perpendicular directions in terms of mass and stiffness distribution. So if you have a building which is an egg shape in plan, this is of course is not a regular. Okay, it must be more or less a rectangular building. Then the ratio between the width and the depth of the rectangle circumscribing the building is less than 4. So if I have two narrow and long rectangle, again this is not regular. Must be sufficiently compact. Okay, area. Then protrusion and recesses are less than 25% of the total length of the building in the same direction as the protrusion and recession. In other words, you can't have like let's say a balcony which is too big compared to the side. So I can't have something like this. Okay. Or something like this, okay? This protrusion recess should not be present, or should not be too big. Less than 25% of the total length of the building. Also this one. I can have something like this. Okay? But this one should be less, no more than 1/4 of the length. Okay? The floor diaphragm can be considered an in-plane region with respect to the vertical structural members. Yes. Then regularity and elevation, all lateral load resisting systems such as wall and frame extended throughout the building height. So we don't have a wall that pops up from the first story, second and third, and there is nothing on the ground level. So the wall should be extended along the whole height of the building. Mass and stiffness remain constant or only gradually decrease along the building side without abrupt changes from the foundation to the top story. The variation between consecutive flow would exceed 20%. The ratio between the actual self-extent capacity and self-extent demand does not materially change along the building side. And possible reduction in the building's plan dimension takes place gradually in accordance with the following limits. At each story, the reduction doesn't exceed either 30% of the first story, dimension 10% of the dimension of the floor just in the mix. So we can't have building like this, or even worse, building like this. Okay, you understand the picture. Okay. We could have it, but then we are no longer regular in elevation. So in your case, just keep a very simple straight building. So, if both plan and elevation regularity criteria are satisfied, the linear static analysis can be used, which is what we want to use it. Because the linear dynamic analysis, you are going to learn the linear dynamic analysis next year in the first semester when doing dynamical structures. Okay? Now, seismic force calculation, we need to calculate what we call the seismic weight. So the seismic weight is the summation of the permanent loads, so structural and non-structural loads, plus the variable loads multiplied by this reduction coefficient. This reduction coefficient is basically equal to psi 2, psi 2. Psi 2 is the coefficient for quasi-permanent load condition. So basically the seismic weight is the sum of all the permanent loads, structural and non-structural, plus the variable loads multiplied by 0.3 if you are in a normal floor, or even by 0 if you are, in terms of snow, if you are in a region which is in a place which is not higher than 1000 meters. You see, neve, snow, below 1000 meters, psi 2 equal to 0. So even if you design l'Aquila, you are without snow on the top. Even so, if you remember last time we had the earthquake in 2016, on the other part of the Gran Sasso, there was 2 meters of snow. Also in places fairly low. However, the earthquake was not so strong at the end. Fortunately, we didn't have a combination of the full snow load with the full earthquake load, because otherwise we might have some problem. Okay, so what we need to do now is the load assessment. So first of all, we calculate the vertical load. So we start from the first story. So first story, we have a 3-story building. So 1, 2, and 3. So first story, second story, the roof. First story, the sizing plan of the building is 6.935 times 6.935, so square, times the permanent load per unit of area, so times 3.56. So this is the weight of the permanent loads on the floor. Plus, here we have 6.935, 2.8 times 6.935 times 4. What is this? So this should be basically the so this is 6.935, this is the wall, one here, 6.935 times 4, because we have 4 sides, times 2.8. To go back to 2.8, 2.8, you see, is the total permanent load per meter of length. So the total permanent load per meter of length of wall is 2.8. So we need to multiply 2.8 by the total perimeter of the walls. So by 6.935 times 4, if we just ignore the openings of the window here, plus 2.8. 2.8, so 2.8 times 2.4 times 2. So this is 2.8, this interior wall, times 2, because we have 2 interior walls, times again, it's 2.4 times 2, this is the total length, times 2.8, the total weight per meter of wall. So 262.31. The variable one is, again, the area, so 6.935 plus 6.935 times 2, which is the variable load, times 0.3, which is this reduction coefficient. So 262 plus 28, 291.16. Second story, exactly the same. So it doesn't, the story doesn't change, the plan doesn't change from the first to the second. Roof, we have something different. The roof, of course, the permanent load is 1.35, not longer 3.56. Then the size is 7.723 times 7.96, because the roof is slightly bigger. Plus, here we have 2.8 is the weight of the wall per unit of length, times 6.935 times 4, so the whole perimeter, plus 2.4 times 2 times 2.8, all divided by 2. Why divided by 2? Because the weight of the wall are calculated this way. So on a building like this, the idea is that when I calculate an intermediate floor like this, I consider half of the weight that are above the floor and half of the weight that are below the floor. So in the end, I can consider the total height of the wall. Same thing here, half and half. But of course, on a roof, I have only half weight of the wall underneath the roof, because I don't have anything above the roof. So for the roof, you see here that I have to divide this quantity inside the bracket has to be divided by 2, because I have only the half below, I don't have anything above. The snow, since we are below 1,000 meters, as you can see here, the snow would be 1.2, but the coefficient side 2 is 0. So there is no snow contribution here at the earthquake. So I have this is what I call seismic weight. I sum up the seismic weight of the 3-story, I get 710.83 kilonewtons. So this is the seismic weight of the whole building, 710 kilonewtons. Fairly low compared to a reinforced building. Okay. Now, to calculate the seismic force, first of all, I need to calculate the first natural vibration period of the building. So the first natural vibration period of the building, according to the Italian regulation, is this formula here, which is based on assessment the total lateral displacement of the building, which may be a bit complex because, as we said before, it's not so simple. You need to know the whole building, you need to know the flexibility and so on. So for this case, we can use the formula suggested in the new draft of Eurocode 8, which is basically the same formula that was proposed before by the Italian regulation, by the whole Italian regulation. So it's 0.05 times the height of the building to the power of 3 divided by 4. So in our case, we calculate this product and we get 0.28 seconds. Of course, the natural vibration period, the first vibration period of the building is needed now to find out, to enter the spectrum and to find out the value of the base shear force. Okay, I think we're probably late enough to stop here, and I think tomorrow morning, when we are a bit more refreshed, we start from here and we continue, we try to finish two working sessions. So please tomorrow remember to bring with you mobile or iPad or whatever is needed to do this kind of survey. Okay? Thank you. See you tomorrow.
Cheers.